Okay, backtracking. Okay, and we have for problem 60, we have a cylindrical tank with a length of 5 feet and a radius of 3 feet to be situated with its axis horizontal. And we have a circular hole, okay, to be cut out, okay, from the bottom. Okay, and that circular hole is going to be with a radius of 1 inch. And now the tank is initially half full of xylene, and we're asking about how long it's going to take for the liquid to drain completely. Okay, so we have okay, so for the cylindrical tank, okay, so it's going to be on its side, and we have a hole to be cut out, and we'll go ahead and take the area. Okay, so you have a 1 inch hole. And with pi r squared, so we're looking at pi times the square of 1/12 of a foot. So we have pi over 144. Now, and we have for the tank, again, from end to end, okay, so you have 5 feet. And we have for the radius of the tank, okay, that is going to be at 3 feet. Well, guess what? We have initially the tank to be half full of xylene. Not filled, okay, but half full. So you have with the initial liquid level, we have y naught, okay, is equal to 3. All right, now looking at what we have, say, from the side view. Again, we have with the tank. Okay, so it has a radius of 3 feet. And we'll say that we have the tank in the process of draining. So once it starts draining, okay, we're looking at, okay, the elevation to be below the middle of this tank. Well, we're starting in the middle, and we have just going down. Okay, so we have a bit of a triangular formation. Okay, so we've got with the tank itself. Okay, so from the middle to any point on the edge. Okay, so we have 3 feet. And for this triangular section, okay, just the elevation. Okay, so we've got the liquid level. Okay, as the tank is being drained, okay, the liquid level is no longer at 3. Okay, but it's just going to be changing over to a different liquid level amount. And for this leg of the triangle formation, so we're looking at 3 feet minus the liquid level. And we have at the base, we have r. So we have a right triangle. You can see you have 3 minus y, and r, and performing what we have with the right triangle geometry is have the square of the radius plus the square of 3 minus y is equal to 3 squared. So I have r squared plus 9 minus 6y plus y squared is equal to 9. I'm getting the 9's to cancel. And once we isolate r squared, so r squared is equal to 6y minus y squared. And r is going to be equal to the positive of the square root of 6y minus y squared. Okay, so we had this set up, okay, arranged whereupon the determination of the liquid radius, okay, was again originated or developed from looking at the side or lateral view. Now where the cross-sectional area is going to come in, so we have with the overhead view, now when we had hemispherical and spherical tanks, the overhead view was circular. But in the case of what we have with the cylindrical tank on its side, now if it had been standing up, we would have another circular overhead view. But this time around, with it laid on its side, okay, the view is going to be rectangular. And for the overhead view, okay, so you have, okay, what is the height of the tank whenever it's standing up, okay, to be the length. Okay, so you have 5 feet. And for what we have in terms of the width portion, okay, that is going to be the same as 2 times the radius, or the diameter of the cylindrical tank. Okay, so in the case of what we have here, so we're going to have the visually, again, we have the width is equal to the diameter and the diameter is going to be 2 times the radius, and we are going to have 2 times the square root of 6y minus y squared. And we have with the cross-sectional area, okay, so you got length times width. Length is at 5. And the width, okay, we have 2 times the square root of 6y minus y squared. So we have for the cross-sectional area, we're going to have 10 times the square root of 6y minus y squared. And the radical remains because we don't have any squaring of the radical involved, as was the case when we had the overhead view to be circular. Instead, we had this time rectangular. Okay, now for what we have looking at Torricelli's law, so you have a of y dy over dt is equal to negative a times, okay, the square root of 2gy, and filling in, so we have 10 times the square root of 6y minus y squared dy over dt, and we have this equal to the negative, okay, circular whole area, we have again negative pi over 144, and going back to the English units, okay, so g again is going to be at 32, and for what we have in following through, okay, so we got 10 times the square root of 6y minus y squared dy over dt, and I can simplify what I have on the right, because you have again square root of 64 is 8 over 144 would be 1/18, so we would have negative pi over 18 times the square root of y. And if I go ahead and multiply the equation by negative 18 over pi, just to get the square root of y by itself, So on the left, and we have negative 180 over pi times the square root of 6y minus y squared dy over dt is equal to the square root of y. And separating the variables, okay, and we have in the process dividing by the square root of y and multiplying by dt, and we're going to have in the rewrite, we have negative 180 over pi, and now for the radical, we can say we have the square root of 6y minus y squared over y, like 6y over y becomes 6, and we have y squared divided by y inside the radical. Okay, that's going to leave us with the subtraction of y. And upon separating, okay, we can integrate. And just moving a bit to the side here. So we have negative 180 over pi. And say we have times the integral. Now for the square root of 6 minus y, we can write this as 6 minus y to the 1/2. And be careful with the signs. Okay, so if I were to utilize u substitution, so we have that u is equal to 6 minus y, and we have du is equal to negative dy, or dy is equal to negative du. So we have in the arrangement, so we have negative 180 over pi times the integral. Here we have u to the 1/2 and again we have times the negative of du. And guess what? Negatives will cancel out here. And so we have 180 over pi. And we have times 2/3 of u to the 3/2 followed by the constant. And simplifying, okay, so we have 120 over pi, and back substituting, okay, for u to the 3/2, that's going to be the quantity of 6 minus y raised to the 3/2 followed by the constant. So transferring back, okay, so the left hand side of the equation we have 120 over pi times the quantity of 6 minus y raised to the 3/2 is equal to t plus c. Now, again, the tank is initially half full. Again, it's going back to our tank. Okay, so you had initially half full. If it had been full, we would have had the liquid level to be at 6. Okay, but for what we have, a y naught equal to 3. So if I were to plug in, okay, we'd have 120 over pi times the quantity. So we have 6 minus 3 raised to the 3/2. Okay, and t is at 0. And let's say that rounding to about the nearest decimal place. So you have like 3 to the 3/2 times 120 divided by pi. And we have for the value of c, we have right at 198.5. And when the tank is empty, again, we have y of t is equal to 0. And for what we're going to have in this result, so you have 120 over pi times what's going to be 6 to the 3 halves. Notice that the variable expression is not y if we have everything going to 0, like what was the case, the hemispherical and the spherical tanks. So yeah, 120 times 6 to the 3 halves over pi is equal to t plus 198.5. And also what's going to happen, okay, so once you get this to a decimal and take away 198.5, you have t to be somewhere around 362.9 seconds. And translating in terms of minutes and seconds, we end up right at 6 minutes and 3 seconds.